Okay, I hope I am clearly audible. Okay, so let's continue. So far we have discussed about Henry's law, and on previous turn we discussed about Henry's law, which is sort of very important. And if we talk about our CBSE examination or ISC examination, so from examination point of view, application of Henry's law is very important, especially the one especially the examples which are very important from examination point of view is first is carbonated drinks and second is scuba diver case, that why they have bent. So this we have already discussed. Why? Because the gas the gas carried into the oxygen cylinder, that we call it as oxygen cylinder, so it's not containing pure oxygen, it contains nitrogen along with oxygen. So as scuba divers go deep into the oceans or sea, they experience more pressure, and this nitrogen is soluble in our blood. As soon as the scuba diver reaches to the surface of the sea or ocean, so solubility decreases and it creates small bubbles, and that because of the formation of that small bubbles in our blood vessels, that produces very bad pain, and that we call it as bent. So remember these two applications which are very important. So let's start with our today's topic. Okay, so our today's topic is like this topic also we have discussed in previous lecture, lattice energy and hydration energy. We all know that what is this lattice energy. So lattice energy is the amount of energy required to break 1 mole of ionic bond. Okay, so lattice energy is something which we call it as endothermic process, whereas in case of hydration energy, this is something which is exothermic in nature. Okay, now, so did you observe this? And it's a very common thing, and we all have observed this, that whenever any liquid is kept in an open vessel and is exposed to sky, or simply it's exposed, that's it. So what we'll notice that after some time there is decrease in the volume of the liquid, and this decrease in the volume of the liquid is because of the phenomenon we call it as evaporation, and the same phenomenon we use for extracting salt from sea water or from brine. So this process we call it as evaporation, and reverse of evaporation also exists. And what is that? Suppose we have vapors, and when these vapors are blocked, so what happens? After cooling down, it changes into what? It changes into liquid phase, and this phenomenon we call it as what? This phenomenon we call it as condensation. ठीक है? So this phenomenon we call it as condensation. अब condensation को एक, अगर हम geographical term है condensation, even we use in physics as well as in chemistry, लेकिन rain को, raining जो process होता है, that process can also be called as condensation or precipitation. तो इट्स अ जोग्राफिकल टर्म, कुछ ज़्यादा ही सॉफिस्टिकेटेड साइंटिफिक वर्ड हो जाता है रेनिंग को अगर हम बोलते हैं प्रेसिपिटेशन और कंडेंसेशन, बट बोथ कैन बी यूज्ड फॉर रेनिंग. Okay, so this condensation is clear. So here liquid is placed in a closed vessel. After some time it is observed that droplets of liquid can be collected on the walls. This process we call it as condensation. Then when a vessel is connected to a manometer, you know what is this manometer? Manometer is a device which we use to measure the pressure. Manometer hai, and the second is barometer. So these two we use in order to calculate or in order to measure the pressure. Okay, so here when a vessel is connected to a manometer, the liquid level in it raises, indicating that there is effect of pressure on the vapor of the liquid exerts the pressure on liquid in the manometer column, and this rise in manometer column indicates us about the pressure that is exerted by vapor, and this pressure we call it as vapor pressure because it is exerted by vapors only. The pressure exerted by the vapor over liquid surface where there exists an equilibrium between vapor and liquid at a particular temperature is called a vapor pressure. So simply in simple terms also you can just remember that what is this vapor pressure? Vapor pressure is simply pressure exerted by the vapor on the surface of the container, on the surface of the walls of the container, or on the surface of the liquid. Okay, different liquids have different vapor pressure. Why? Because if we like talk about one term, that is volatility or volatile, so different liquids have different tendency towards volatile. Petrol is highly volatile, and if we compare petrol and water, so both have good difference towards their volatile property. Petrol is highly volatile, water is also volatile, but rate of like evaporation of water is little slow as compared to the petrol. So somewhere it depends on nature. This is the first thing, nature of the like substance or liquid, and the second is the temperature, because as the temperature increases, vapor formation increases, and if vapor formation is taking place at a higher rate, so it will exert more pressure also. This is the first thing. Do you know the reason behind this? So we better know the reason why. Where we have studied these things in grade 9 in chapter states of matter. So the attractive force between molecules are different depending upon the nature of liquid, and lesser or weaker the attractive force, easier will be evaporation. So lattice energy and hydration energy are respectively exothermic, and exothermic. So what should be the answer here? Like we started with this only. Lattice energy is the amount of energy that we give. So it is endothermic, and hydration energy is the amount of energy that is released when any substance is added into water. Now vapor pressure of liquid solutions. So vapor pressure of liquid solutions. So here we have to discuss about liquid solutions. So liquid solutions are formed when solvent is a liquid and the solute can be a gas, liquid, or a gas. So this we have discussed in lecture 1 only, that like state or physical state of a solution is decided by the physical state of solvent. If solvent is liquid, so solution is also liquid in nature. The solution containing two components are called as binary solution, solute solvent, binary. These are liquids in liquids, solids in liquids. These are the cases that we have to discuss: liquids in liquids and solids in liquids. A binary solution containing two volatile liquids. Remember here, binary solutions we have. Binary solutions means two components, and both the components are volatile in nature. Means both changes into what? Both changes into vapor. So here in such cases, these are components taken as 1 and 2 in a closed vessel. So both are changing into vapor. So both will exert pressure on the walls of the container. Vapor phase, liquid phase. Both the component vaporizes and equilibrium state is established between vapor phase and liquid phase. So here vapor phase, this is liquid phase. And in a binary solution of two liquids, let us say P1 be the partial pressure of the first component and P2 be the partial pressure of the vapor, like partial pressure of the component 2, and total pressure exerted on the walls of the container is equal to the sum of partial pressures of component 1 and component 2. So the total vapor pressure here, total is equal to sum, that we have already discussed. So P total equals to P1 plus P2. And which law, which law we have applied here? So this is, we call it as Dalton's law of partial pressure. The partial pressure are related to mole fractions. The term itself suggests that partial means part of pressure exerted by some component. Partial pressure means this part of pressure exerted by some component of the solution. If P1, P2, P3 are the partial pressure of the partial pressures, then total pressure will be what? Again, which law we are applying here? We are applying here Dalton's law of partial pressure, according to which total pressure exerted on the walls of the container is equal to the sum of the partial pressure of the individual gases. So here P total P1 plus P2 plus P3 only, right? P total. So first is the correct answer. Raoult's law, and this Raoult's law is very important. And after discussing about Henry's law, we need to know about some mathematical expression. We were in need of some mathematical expression which can be used in place of Henry's law. So this Raoult's law is what? This Raoult's law is basically modified version or modification of Henry's law. So what does this law states? If we talk about this law, so Raoult's law, according to this Raoult's law, it states that the partial vapor pressure of each component in the solution of a volatile liquid is directly proportional to the mole fraction of it in the solution. Means the vapor pressure of the component is directly proportional to the mole fraction of that component present in the solution. It means here mathematically it can be written as P1 is directly proportional to chi1, where this chi or x we call it as mole fraction. Then P2, this is second component, partial pressure of second component is directly proportional to the mole fraction of second component. So chi1 and chi2 are the sum of mole fractions. Chi1 and chi2 are mole fraction, and we have to find out the total number of moles here. So how we can find out? Simply chi1 plus chi2. So P1 equals to what? P1 equals to P1 naught into chi1. What is this P1 naught? So if we talk about this P1 naught, just a second. So this P1 is what? This P1 we call it as what? This is the partial pressure of this component in its pure form. So this P1 equals to P1 naught into chi1. Okay. Similarly, P2 equals to P2 equals to P2 naught into chi2, and this is for what? This is for second component, and let us say this is our equation 2. So P1 and P2 are the vapor pressures of the component in its pure form or pure state. So according to the Dalton's law, what we say, total pressure equals to the sum of the partial vapor pressure. So P total equals to P1 plus P2, where we'll replace this P1 and P2. So P1 will be replaced by P1 naught into chi1, P1 naught into chi1 plus P2 naught into chi2. Sum of the mole fraction of chi1 plus chi2 equals to 1 only. So chi1 equals to 1 minus chi2. How we have written this? So we know that the sum of mole fractions of all the component is equal to unity. So simply what we have done, we have transposed this x2 on right hand side, and here we are getting chi1 equals to 1 minus x2. Okay. Therefore, P total equals to what? P total equals to 1 minus chi2 P1 naught plus P2 naught into chi2. So here this expression is written in terms of what? This expression is written in terms of one mole fraction of one component only. So here it becomes P1 naught minus chi 2 P1 naught plus P2 naught into chi 2, and simply it can be written as what? P total equals to 1 minus chi 2 P1 naught chi 2. Yes, this can be written as like this also, chi 2 P2 minus P1 naught. Okay, so I'm moving to the next slide. From the above equation, the following conclusion can be drawn. Total vapor pressure over the solution can be related to the mole fraction of any component, that we have already done. Total vapor pressure over the solution varies linearly with the mole fraction of the component 1 or 2. Like vapor pressure is depending up linearly upon mole fraction. If mole fraction is increasing, so vapor pressure will also increase, and this increase will be what? It will be linear. Depending on the vapor pressure of the pure component 1 and 2, total vapor pressure over the solutions either decreases or increases with the increase of the mole fraction of either component 1 or 2. So it totally depends on what? It totally depends on the mole fraction of the component. Let us see this. This graph is very important to understand. So just focus at this point. This is chi 1 and this is chi 1 again, and here like in downwards we have written chi 2 equals to 0, and here chi 2 equals to 1. So if you notice here, so what we have here, so if you notice here, so while moving from left to right, chi 1 is chi 1 is decreasing, and this chi 2 is, while moving from left to right, is increasing. And the linear change is somehow like this only. Suppose this is vapor pressure. On this axis we have drawn vapor pressure, and on this axis we are drawing mole fraction. So this linear change is like this only. Okay, so here also the linear change is shown. This is chi 1. Chi 1 is maximum, and while moving from left to right, this chi 1 is decreasing. Chi 2 is least, and while moving from left to right, its value is maximum, right? So here what we are observing, when chi 1 mole fraction is maximum, it's maximum, it can be 1 only. In that case, P1 naught pressure is maximum. P1 means it is in pure state. Similarly, here in case of chi 2, when it is 1, it means only chi 2, means only second component is there. So whatever vapor pressure in that condition we get, we call it as vapor pressure for pure component, pure vapor, like vapor pressure for pure component, for pure second component. P1 naught is vapor pressure in pure state for component 1. So as we can see, as the mole fraction starts changing, it starts decreasing. So here partial pressure is also starts decreasing. Here as you can see, mole fraction starts increasing for second component, and vapor pressure also starts increasing for the second component. So this graph is very easy, but most of the time students find it very difficult to understand, but although it's easy. So this is graphical representation of vapor pressure versus mole fraction of an ideal solution. So this is another, and this is for ideal solution. The thick line curve represents the total vapor pressure of the component. Huh. Like this dotted line is representing what? This dotted line representing for individual component. Like this is for component 1, this this is for component 2, and this, the continuous line, is here considered as third, only third component, but it is dealing with the mixture like sum total. So how this total is varying with change in mole fraction, so it is mentioned by this curve 3. The minimum value of the p total is equal to p1 naught and the maximum value equal to p2 naught, that is p1 naught is smaller than p2 naught. Using the Dalton's law of partial pressure, we can find out mathematical expression partial pressure equals to mole fraction into total pressure. Pi equals to chi I into P. Very important point, this is the composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the component. If Y1 and Y2 are the mole fractions of the component 1 and 2 respectively in the vapor phase, then using Dalton's law we can easily find out P1 equals to Y1 into P total, where Y1 is what? Y1 are mole fraction, and P2 equals to Y2 is again mole fraction, and P total we have. Raoult's law, a special case of Henry's law. This we have already discussed, but how? The partial pressure of the volatile component or a gas is directly proportional to its mole fraction in solution. This we have discussed, right? Therefore, P is directly proportional to chi and P equals to P naught. Like in case of Raoult's law, it was P naught into chi, but here in case of Henry's law, this P equals to KH, where KH was Henry's constant. Okay, and we were having like controversies were there related to this KH only. Okay, so P equals to partial pressure of the gas, chi is mole fraction of its solution or any component, KH is Henry's constant, where K becomes equal to P1 naught. Okay, so rate of evaporation depends upon nature of liquid, surface area of the liquid, temperature, flow of air current over the surface. So it depends on what? Rate of evaporation. It depends on nature of liquid, surface area of the liquid, temperature, every, like the correct answer is A, B, only two, B, C only, A, B, C only, or A, B, C, D. So A, B, C is correct. Flow of air current, so somewhere it depends on what? Somewhere it depends on wind or air current also, so the correct answer will be 4, that is A, B, C and D. Raoult's law part 2. So vapor pressure of chloroform, listen, chloroform dichloromethane at 298 Kelvin are 200 mm and 415 mm, right? Let us write. So as you can see here, we have so 200 mm and 415 mm of Hg. Calculate the vapor phase of solution prepared by mixing 25.5 gram of CHCl3 and 40 gram of CH2Cl2. So first of all we'll find out what? First of all we'll find out the moles, number of moles, and then mole fraction. So here first we'll calculate the moles and then mole fraction. And here in case in pure state it's already given, so simply which formula will be using? P equals to P naught chi only, this formula will be using. So let us solve this question. So molar mass of CHCl3 is how much? It's 119.5. Molar mass of CH2Cl2 is how much? It is 85 grams. And then number of moles of CHCl3. So first we are finding out the number of moles. So formula we all know, weight upon molar mass, and how much mass is given? 25.5 gram divided by 119.5. So this is going to give us how much? 0.213 moles. Number of moles of CH2Cl2, so here we have 40 grams and molar mass is how much? Molar mass is 85 grams. So here in this case 40 divided by 85, so this equals to what? 0.47. So in order to find out the mole fraction, what we do, in order to find out, suppose we have two components, component 1 and component 2. So n1 or chi, sorry, I'll just replace it by chi only. Let us say mole fraction as chi1. So chi1 equals to n1 upon n1 plus n2, and in order to find out chi2, what we do, n2 upon n1 plus n2, or we can do chi2 equals to 1 minus chi1 simply. So here we are getting total number of moles 0.213 plus 0.47, and then total number of mole is 0.683 moles, and mole fraction of CHCl3 will be 0.213 divided by 0.683, so it is 0.312, and in case of CH2Cl2 0.47 divided by 0.683, so 0.688 upon, like this is only the mole fraction. And now what we have to do, using equation P total equals to P1 plus P2, this can also be used. So P total 200 is given, already given, P2 minus P1, so 415 minus 200 into 0.688, so this will give us 200 plus 147.9 or 347.9 mm of Hg. So this will be the total pressure exerted by the volatile mixture of chloroform and dichloromethane. Vapor phase of solution of solid in liquid. This is another case. Vapor pressure of solution of solid in liquid. So vapor pressure. So the pressure exerted by the vapor molecule of a liquid when they are in equilibrium with the liquid of a given temperature is called vapor pressure of the liquid at that temperature, because solids do not undergo evaporation. So here the vapor pressure will be formed, or vapors will be formed because of this liquids only. Vapor pressure of the liquid is measured by the barometric method or barometer. So the vapor pressure of the solution is always less than that of pure solvent. Remember this. In solution, some of the non-volatile solutes are there. Non-volatile solute means what? Non-volatile solute means which does not undergo evaporation, like salt. So in case of salt, what happens? We collect water from sea. समुंदर से पानी लिया, ओशन से पानी लिया, हमने इसको गड्ढे में रख दिया. So after some time we'll observe that water is evaporated because water is volatile in nature, but salt क्या होते हैं ना, सफ़ेद सफ़ेद, वो वहीं इकट्ठे हो जाते हैं because it is solid and it is non volatile in nature. ठीक है. टैप वाटर लेते हैं, टैप वाटर को हम रखते हैं स्पून, स्पून पे छोटा स्पून, टी स्पून लेते हैं, उस पर रखते हैं, and after some time we'll notice that water is evaporated and there will be shade present on the spoon surface, and that shade is because of the presence of mineral or contamination in water, which is many a times good, but if it is highly contaminated, so it is very harmful for us. So therefore the fraction of the surface covered by the surface solvent molecules get reduced. So the vapor pressure of the solution is always less than that of the pure liquid. So this is pure solvent and this is solute, solvent and solution. Remember here what we have done here, as you can see, surface is occupied by what? Surface is occupied by the non-volatile particles. This is what? This is non-volatile. And once the surface is occupied So it reduces the rate of evaporation. That's why vapor pressure is maximum in pure state only, or pure solvent. The decrease in vapor pressure of the solvent depends on the quantity of non-volatile solute present in the solution. एंड कितना ज़्यादा डिक्रीज होगा वो डिपेंड करेगा किस पे, वो डिपेंड करेगा किस पे, वो डिपेंड करेगा अमाउंट पे, अमाउंट ऑफ नॉन वोलाटाइल सोल्यूट पार्टिकल्स दैट वी आर taking. Example, 1 mole of urea is dissolved in 1 kilogram of water exerting vapor pressure is same as that of 1 mole of sucrose is dissolved in 1 kg of water at the same temperature. Raoult's law is in general for any solution, the partial pressure of each volatile component in the solution is directly proportional to the mole fraction of that component. So Pi is directly proportional to chi I, where I are the number of components, and Pi equals to Pi naught into chi I. So P1 naught or Pi naught is proportionality constant. It is equal to vapor pressure of pure solvent. So if we plot a graph between this and mole fraction, so this is what, this is one graph. This is, as you can see, mole fraction of the solvent, which is volatile in nature and which is 0, and as it increases from 0 to 1, vapor pressure is linearly increasing. Remember, from here we can expect MCQ in exam. Okay, as temperature increases, vapor pressure of a liquid increases linearly, decreases linearly, increases exponentially, decreases exponentially. So what should be the answer? Answer is increases. Uh, answer should be this only. Okay, so that's all for in this lecture, Raoult's law, which is very important. So its application is important. No direct questions will be asked, and on the basis of this Raoult's law only, we are going to discuss about ideal solutions, that what are ideal solutions and non-ideal solutions. So in the next lecture we'll be discussing in the next lecture we'll be discussing about ideal and non-ideal solution. So for today, that's all for this lecture. Thank you. Have a good day.